Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories. The man who redefined the universe, Martin Rees' groundbreaking discoveries. He said that the probability of humans making it to the year 2100 is only about 50%. Pause for a second. It's not because of an asteroid hitting Earth. It's not because aliens are invading. It's us, more specifically, it's our technology and our choices. And the person saying this isn't a conspiracy theorist. He's Martin Rees, a British astronomer, the former head of the Royal Society, and the master of Trinity College, Cambridge. With all these titles, you could say he's one of the people who knows the universe the best. Now, here's the question: why, as someone who spends his days studying the cosmos, is he so worried about Earth? This is someone who's seen black holes, studied the birth of the universe, and calculated how galaxies evolved. You'd think, as a surface-level creature in his eyes, that humans wouldn't even make his radar. But here's the kicker: he's most concerned about us, and not some far-off day in the future. No. He's talking about this century, the very 100 years you're living through right now. He says this is the most dangerous time in human history. Dangerous to what degree? Dangerous enough that we now have the power to wipe ourselves out completely. Not a slow extinction, but an all-clear button. Nuclear weapons, biotechnology, artificial intelligence. Sounds cool, right? But when you put all that together, it's like sticking a rocket engine on a car that has no brakes. What makes it worse? The people in the car are unstable. This isn't science fiction. It's reality, and this is the core message he keeps repeating: the speed of technological advancement has outpaced our ability to manage the risks. To put it simply, we create things, but we don't always know how to use them safely. It's like giving a child the nuclear button, and they think it's a toy. Now, a lot of people might hear this and think, isn't he being a little too pessimistic? But here's the thing: he wasn't posting this on social media. He said all of this in a serious scientific setting, speaking in a calm tone, making a rational judgment. No drama, no exaggeration, just one conclusion: if we're not careful enough, this century might just be humanity's shortest one. And so the question becomes very direct: why would someone who studies the universe be so concerned about the future of humanity? Let's rewind to 1942. The world is still at war, the sound of artillery is in the air, and above the skies of England, it's not stars, it's bombers. This is the backdrop against which Martin Rees was born, in a small, quiet corner of Yorkshire, England. Not in London, not in some academic hub, just an ordinary, peaceful place. And how ordinary was it? Well, his childhood didn't show any signs of him becoming a future cosmologist. His parents, they were teachers, not scientists, not engineers, not the kind of folks building rockets in their basement. There was no lab, no telescope, and definitely no "you're going to change the world" pep talk. It was more like study hard, don't be late. That's where he started. No genius label. No childhood miracles. No, I've been thinking about the origin of the universe since I was 5. If you had to pick one thing about him as a kid, it was that he was very quiet. How quiet? While others were looking up at the stars, he was looking down at formulas. While others were dreaming of the universe, he was crunching numbers. Romantic? Not at all. His idea of romance was probably solving a math problem right, and feeling a little aha moment inside. That was his happiness. Post-war Britain wasn't all that romantic either. The war ended in 1945, but resources were scarce, and society was rebuilding. In such an environment, the first thing you learned wasn't to dream, but to face reality, and that reality was simple: work hard, learn step by step. And that's how he learned too. At school, he did well, especially in math, not the genius steals the show kind, but more of the steady output type, calm, precise, like a computer with no emotions. Teachers loved him, classmates, not always. After all, when you're still struggling with one problem, he's already finished 3 pages of calculations, and he's still checking. It's a little discouraging, isn't it? But here's the key: he didn't end up on the Cosmos track right away. Important to note, when he was younger, he didn't plan on studying the universe. No, I want to be an astronomer dream. In fact, he didn't even care much about the stars. Sounds counterintuitive, doesn't it? A future cosmologist, who wasn't even fascinated by the cosmos as a kid. It's like a future Michelin star chef who was just really good at chopping potatoes as a kid. No big dream, just solid skills. By 1960, he was 18. And he made a decision: he was going to Cambridge, specifically Trinity College. It sounds like the perfect place for high achievers, right? It was where Isaac Newton studied. A place full of brilliant minds, and yes, that pressure. But instead of being intimidated, he thrived. Why? Because there, he found something he loved: math, pure, clean. No noise, no emotions, just logic. If the world was a machine, math was its instruction manual. He studied hard, very hard, while others were staying up late to meet deadlines. He was up because he hadn't finished one of his math problems yet. Sounds a little self-punishing, doesn't it? But to him, that was fun. In 1963, he graduated with a degree in mathematics. Everything seemed to be going perfectly: a good student, good grades, good school. And then, what's next? Normally, he could have stuck to pure math, or gone into applied sciences, or even made money in finance using his math skills. But here's the twist: the story took a turn. He didn't have it all figured out. No clear direction. No ultimate goal. But something was happening. The formulas, the abstract reasoning, they were starting to point somewhere, and that somewhere was the universe. Those stars he never cared about before, those distant celestial bodies, suddenly became a problem. A problem he could solve with math. Now that's different. When the universe turned into a math problem, he got interested, and not because it was romantic, but because it was difficult, and very difficult, difficult enough to get addictive. See, he wasn't drawn to the stars. He was drawn to the problem. To the complexity. To the unsolvable. And the universe, it ticked all the boxes. When you look back, the quiet boy, the one who loved formulas, he was preparing all along, not for some dream, but for a problem that hadn't even appeared yet. And that problem, it was about to change everything. In 1968, he just earned his PhD, but before he could even catch his breath, he was thrown into an even bigger world. First stop, Caltech. That's California, by the way, and it's not just sunny there. It's sunny, and the minds? Well, they're even brighter. The people at Caltech, they're not just doing research. They're redefining research. The moment he stepped in, he felt the atmosphere, and it wasn't the air. It was the IQ. Walk into any office, and you might find a future Nobel laureate. Sit in on any discussion, and it could be the birthplace of a new theory. This wasn't just a university. It was more like a brainpower concentration camp, and he didn't crack under pressure. In fact, he adapted quickly. Why? Because they spoke the same language: math, logic, and an obsession with the unknown. He started collaborating with top physicists, talking black holes, high-energy astrophysics, and the kind of questions that would make most people click away from the video, but not here. Those questions were everyday conversation. By 1969, he was on the move again. This time, Princeton University. The pace kept picking up. The environment, it was different, quieter, deeper, like a well. So deep you drop a question in, and the echo takes a while to come back, but when it does, it's usually much closer to the truth. At Princeton, he delved deeper into core theoretical physics issues: gravity, the structure of the universe, and the role of black holes, which were becoming more and more significant. Back then, black holes hadn't exactly gone mainstream. There were no blockbuster movies about them. No pop culture references. Heck, a lot of people were still debating whether they even existed, but he was already studying them seriously, not as a story, but as a physical object. By 1970, still at Princeton, he was absorbing and outputting more than ever. This period, think of it like a series of ever harder game levels, and the stakes kept rising, but with every level, his experience kept growing. Then in 1971, he was back at Caltech for the second time, and this time, it was different. The first time, he was a new player. This time, he had his own ideas, his own research direction, and he was starting to influence others. That was the key. He wasn't just a learner anymore. He'd become a participant. A driver. He wasn't just listening. He was speaking, and when he spoke, people listened. In 1972, he moved to Harvard University. If the previous places were like intense training camps, Harvard felt like the championship final: top resources, top talent, top competition. But by now, he was used to this environment, and maybe even a little bit enjoying it, because every conversation, it was pushing him closer to answers. Or, better yet, pushing him toward better questions. For the next few years, you could sum it up like this: he was on a global scientific tour, not a vacation, but a whirlwind tour of the world's top scientific stages. Every stop, a place where the best minds gathered, and the discussions, well, they were the kind that made your brain hurt. And the most important part, He was starting to get noticed, not because of his titles, but because of his abilities, calm, precise, unpretentious, but every word he said, it carried weight. By the time this phase wrapped up, he wasn't just the young, promising guy anymore. He was a scientist on the verge of greatness. Then, in 1973, everything shifted. At 31, he got something. A chair sounds pretty ordinary, right? But this wasn't just any chair. This chair, it had once been occupied by Isaac Newton. Yeah, that Isaac Newton, the guy who invented classical mechanics, the guy who got hit by an apple and had a moment of genius later. It was occupied by Paul Dirac, the giant of quantum mechanics, then Stephen Hawking, the face of black holes, and now it was his turn. At 31, that number alone is almost absurd, because this chair, it's usually for those who've already proven themselves, but he was just starting to hit his stride. It's like this: while others are still figuring out Excel in their first job, he's already sitting in the boardroom and the legends before him. Yeah, no pressure, but here's the twist: he didn't go in to inherit the past mode. There were no grand speeches, no declarations. He was calm, maybe even too calm, like he was saying, alright, this is a job. But that job, it came with 300 years of scientific history behind it, and the location, Cambridge. A place so rich in scientific history it might as well be called a scientific sanctuary. This place, too many geniuses have walked those halls, too many world-changing formulas have been written on those blackboards, and now he was sitting at one of the most important positions. But the question remained: what was he going to do with it? Keep the tradition alive, stick with the classics, be the qualified successor. If that was the plan, the story would be boring, but that wasn't his choice. He took one last look at the past, and then turned his gaze to the far horizon of the universe, and more specifically, the extreme universe, black holes or quasars, the early structure of the universe. At the time, these weren't mature fields. They were more like unfinished projects, so there were theories, there were guesses, but there was no unified understanding, and what he wanted to do, it wasn't to fill in the gaps. It was to reorganize the pieces so they'd form a clear picture. Sounds grand, right? But his method, simple. Do what he did best: calculate, derive, analyze calmly. No fanfare. No drama, just logic. And so, he started studying the most extreme objects in the universe, those ridiculously bright quasars. Why were they so bright? Where did their energy come from? The answers started to become clearer. Black holes, but not just any black hole, the supermassive black holes, hiding in the centers of galaxies, like silent engines consuming matter, releasing energy, powering entire systems. This way of thinking, it would later become mainstream, but back then, it was still unproven. And he was right in the middle of pushing that proof. That's the difference: some people explain the known, others create the future known. And he was definitely one of the latter. The key thing, he wasn't trapped by his title. A lot of people, once they land in high positions, start playing it safe, because the position's too important, but not him. The higher he climbed, the further he dared to look, because he knew the real risk. It's not making mistakes. It's stopping altogether. So for him, 31 wasn't the end. It wasn't even the peak. It was just the beginning, the gateway to a much bigger stage. What was coming next? It wasn't to preserve what Newton had left behind. It was to answer a far more complicated question: how does the universe work? And where do we fit in? If the earlier years were about laying the groundwork, then now, it's time to hit the accelerator. He wasn't just asking questions anymore. Now, he was providing answers, the kind of answers that, once confirmed, would rewrite textbooks. Let's start with the first one: quasars. In the 1970s, this was still a huge puzzle for astronomers. They were too bright to the point where it made you wonder if physics had gone rogue. But Martin Rees had a simple idea. If the regular mechanisms weren't cutting it, why not use an extreme one? Black holes, but not just any black holes, supermassive ones, the ones that could be 1,000,000, even 1,000,000,000 times the mass of the sun. Here's the key point: a black hole doesn't emit light. It's black, really black. So black, not even light can escape. Then how come quasars are so bright? The answer lies in what happens just before something falls in. When matter gets pulled near a black hole, it forms an accretion disk, spinning at insane speeds. It starts to heat up. Friction makes the temperature soar, and boom, it releases massive amounts of energy. It's like a cosmic power plant, or, better yet, a runaway nuclear reactor. So here's the classic paradox: the brightest things in the universe are coming from the darkest. Sounds like a contradiction, right? But that's physics for you. At first, This model wasn't widely accepted. A lot of people thought it was too radical, but as more observations rolled in, more and more evidence pointed to the same conclusion: quasars, they're black holes feeding. Now, it's the standard model, but back then, it was a breakthrough. Let's step back for a moment. The next question wasn't just about a single object. It was about the entire structure of the universe. In the early days, the universe was nearly uniform, like a pot of soup that's just been stirred. No structure, no layers. So how did we get galaxies, galaxy clusters, and the vast cosmic web we see today? Martin Rees's approach, cool-headed as always. He started small, from tiny fluctuations. The early universe wasn't completely uniform. There were subtle density differences, so tiny you could barely notice them. But gravity doesn't care about size. In denser regions, gravity is stronger, and that starts pulling in more matter. The more it pulls, the denser it gets. It's like a snowball effect. It keeps growing. Eventually, galaxies form, then galaxy clusters, and finally, the cosmic web. In short, the universe wasn't designed. It evolved. There was no blueprint, just the rules. This idea was later strongly supported by observations from the cosmic microwave background radiation to the distribution of large-scale structures. Everything pointed to this conclusion. It wasn't a coincidence. It was a mechanism. Next, things took a darker turn. Gamma-ray bursts, the name alone sounds dangerous, and it's even worse in reality. These are some of the most violent explosions in the universe. The energy released in just a few seconds can surpass the total output of the sun over its entire lifetime. Yeah, seconds, not billions of years. At first, scientists had no clue where they came from, but eventually, the theory started to take shape: massive stars collapsing, or neutron stars merging, forming black holes, and at the same time releasing intense jets of energy. If one of those jets points toward us, we get a gamma-ray burst. In simple terms, the universe occasionally hits the self-destruct button, and Martin Rees, he was one of the first to seriously study these extreme phenomena. He didn't shy away from the extreme, he specialized in it, because that's where the purest physics lies. Let's bring it closer to home now. The Milky Way. There used to be a big question: is there a black hole at the center of our galaxy? Today, we'd all say, of course. But back then, it was still a hypothesis. Martin Rees was one of the early voices saying, yeah, there's definitely a supermassive black hole at the center. Not a small one. A huge one. Hundreds of thousands, maybe even millions of times the mass of the sun. There wasn't direct evidence back then, just indirect clues, and many were skeptical, but Martin stood firm. Later, observational technology improved: radio telescopes, infrared observations, and measurements of star orbits. All the evidence piled up, and eventually, we confirmed it. At the center of our galaxy, there is a supermassive black hole. We call it Sagittarius A star. It went from prediction to fact, and that's one of the best moments in science. But that wasn't all. He did something else too, not proposing a theory, but influencing a huge shift: the multiverse theory. It was always on the fringes. A bit philosophical. People didn't take it seriously, but Martin Rees began to seriously discuss it. He started promoting it, analyzing its scientific significance. He turned it from a mind-bending idea to a discussable scientific question. He didn't say, this is definitely true. But he did say, we shouldn't ignore the possibility. Because if it is true, the implications would be massive. It could change how we understand existence itself. By now, you might notice a trend: everything he worked on, it stretched the boundaries, from black holes to galaxies to the structure of the universe, and even the multiverse. The scale kept growing, the questions kept deepening, and he just kept pushing forward. But here's the interesting part: none of this was the most crazy part, the real unsettling thing. It's not the universe itself, it's humanity. If he spent the first few decades looking outward at the universe, now, he turned his gaze back and to something even trickier: humanity itself. Fast forward to 2003. Martin Rees did something unastronomical. He wrote a book. Its title was Soft. The content? Not so much Our Final Century. Yeah, you heard that right. Our Final Century sounds ominous, right? Most scientists write books on the origin of the universe, on black holes, on galaxies, but not him. He went straight for the ending, and not just any ending, the end of humanity. The twist: he didn't tell a story. He didn't write fiction. He crunched the numbers. He gave a probability point: 50% the chance humanity survives past 2100. It's just half. Sounds like a disaster movie, right? But he says it calmly, even coldly, like it's a weather forecast. Tomorrow, 50% chance of rain. Only, the rain in this case, it's extinction. So, what's he worried about? It's not asteroids. It's not the sun exploding. We've studied these risks, and they seem unlikely in the short term of the real risks. They come from us, nuclear weapons. No need to explain this one. Humanity has already shown we can reset civilization in hours. Then there's biotechnology, especially genetic engineering of viruses used to be naturally occurring. Now, humans can design and even optimize them. This sounds cool, right? Until things go wrong, the spread could outpace our control. And then there's artificial intelligence. Back in the early 2000s, it wasn't as big as it is now, but Martin was already concerned, not about robots ruling the world like in the movies, but the real issues: system complexity, decision-making out of control, and can humanity truly understand what it's creating? Simply put, we're building stronger tools, but we're not sure we can control them, and that's the real risk. He saw these factors stacking up not as a cocktail of fear, but as a logical calculation. Each one, on its own, might not be catastrophic, but together, the risk becomes exponential. It's like this: a match, not dangerous. A can of gasoline, maybe not, but put the two together, and someone lighting up nearby. Now, you've got a problem, and Martin saw that combination. Here's the kicker: these technologies, they're not owned by any one country. They're not controlled by one organization. They're spreading, getting cheaper and easier to access, which means the risks, they're no longer concentrated. They're scattered and harder to manage. A lot of people hear this and think, too pessimistic. But Martin didn't see it that way. He called it realism. First, you see the risks, then you can talk about hope, because if you don't even acknowledge the problem, there's no solution. So he did something new. He started speaking out, not just in academia, but to the public. He started discussions on risk, on the future, on responsibility, because science doesn't just bring power. It brings responsibility. And with that, his identity shifted, not just as an astrophysicist, but as a risk thinker. In fact, he might even be considered the risk analyst for humanity's future. And here's the key point: he wasn't trying to scare people. He wasn't telling disaster stories. He was doing the same thing he'd always done: gathering information, analyzing trends, and making a judgment. The only difference now, the subject wasn't the universe. It was us. He looked at the universe, not at the stars, but at the structure. At the unseen forces of the rules that bind everything together. And for the first time, he made humanity aware the universe isn't a static picture. It's a drama unfolding, and the plot, it's insane. He studied black holes, not the sci-fi scary version, but the real one. More subtle, yet more terrifying, because it exists, and it's sitting right at the center of our galaxy. The theories he helped push forward changed how we saw black holes. They're not the universe's trash cans, they're the engines, the power cores shaping galaxies from the shadows. In one sentence, the universe isn't a light show. It's a system with power structures. The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.